So in addition to having an imperfect risk reduction isn't 100%, we're also removing ovaries in some women unnecessarily. Some women will never develop ovarian cancer, yet we take her ovaries out. So again, this is all argument for the precision piece of this. And with BRCA1 and 2 and ovarian cancer being the poster child for the best that we can do pretty much in cancer, where we have all the pieces in place, we're still not doing really very well because we're intervening in too many women, and we are intervening without success in other women. So that's really depressing, because for 20 years we thought this was going to be the magical case where we knew exactly what to do. And in fact, we do it. It's clinically important. We save lives all the time, but we can do better. We should be able to do better. And again, I'm using this as an example because I think that there will be other situations where it's this complex, where when we want to think about how to precisely intervene on an individual's cancer risk, it's not going to be a simple situation of you have one mutation, now we can do this. More might need to be thought about. So what is that more? What kinds of things might we need to think about in order to make more precise our estimate of risk, and then in whom we want to intervene? So this is an example of work we did a couple years ago that suggests there are mutation-specific risks. That is, you have a BRCA1 mutation, but the risk conferred by that BRCA1 mutation is not the same for every person. So what we found, without going into a lot of the detail, is that there are regions in the red that we are calling ovarian cancer cluster regions, where if your mutation disrupts that region, your BRCA1 mutation disrupts that region, you have a relatively higher risk of ovarian cancer. And if you have a mutation that disrupts the blue regions, you have a relatively higher risk of breast cancer. So the first thing this is telling us is that not all mutations are created equal, and just having a BRCA1 mutation means maybe you have a 57% lifetime risk, but maybe there's variability in that risk that we can explain by something biological, by something that we can measure, like the type of mutation that you have. So here's an example just of translating that work back to risks rather than to see what the mutation-specific penetrations might look like or how they might change. So just as one example, there are lots of these in the papers. Let's say you have a BRCA2 mutation and you want to know what your ovarian cancer risk is. Well, in the gray is the usual risk. That's the 18%. I showed you that number before. BRCA2 associated with ovarian cancer, 18% lifetime risk by age 70. So there's your 18% risk. What we found, as an example, is that if you had an in-frame deletion, a specific type of mutation, your ovarian cancer risk was more like 43% by age 70. So we're talking about mutation-specific risks that are quite different than the average risk in these populations. And so there might be some women, and I don't know what the threshold is there, but 43 could be seen as quite different than 18. And if it were, would that change a woman's or a clinician's decision-making? So we have a grant right now to ask, what is the threshold around which people would actually change their management decisions and things like that? But at least we have a basis to know that 18% risk is pretty big, 43% is much bigger. When would that change somebody's behavior? And we can imagine other things where the 18% risk actually goes down to 6% for non-protein truncating mutations, and et cetera, et cetera. And some of them really aren't all that different, 33 versus 40. Maybe that won't matter to somebody. But suffice it to say that there are plenty of variability that we can measure and understand that we can use to improve our ability to predict risk and then maybe apply preventive strategies. And it gets more complicated. We know that, for example, BRCA1 and 2 are part of very complex biological pathways. BRCA2 is up here, and so we can ask, well, if you have a BRCA2 mutation, but you also have a mutation in one of its interacting genes, it's one of the things that it helped regulate its biological functions, like PALB2 or RAD51 or ATM or BARD1, does that change your risks? That is to say, you have a BRCA2 mutation and you have another mutation in an area that is also, or in a protein that is also potentially impacting on the biology of this risk. And so we can see, for example, just if you have a BRCA2 mutation and a rare ATM variant in the same person, you have a relatively 11-fold increase in risk for ovarian cancer. So BRCA2 gives you an 18% lifetime risk. if you also have this ATM mutation, it's 11-fold higher than that 18% risk. And you can see there's some substantial differences there. So not only do we have mutations in the individual gene, but we may have modifier loci that might impact on risk. And we know that these kinds of relationships are really quite complex. We have all these modifiers, they bind things, and so we can imagine even asking the question, well, what if you had a BRCA1 mutation, a RAD51 mutation that disrupted the nuclear localization signal? So biology, we know what the biology is, we know what these mechanisms are. What if we start disrupting multiple things in these pathways? Well, what we can see, and this is work we're just about to submit, that if you have, let's say, if you only have a mutation in a particular domain, or if you have a mutation in a particular SNP, risk is pretty average. But if you have both, your relative risk of breast cancer in this example goes up almost fourfold. So again, there are all sorts of different levels at which we can start to think about the complexity of an individual's risk and the implications of that risk assessment on the applications of prevention and early detection. And at what point does a fourfold, for example, increased risk in a woman's breast cancer change how we would manage that? Do we need all of this information? Maybe we need more information. Maybe we also need to know her reproductive history and whether she took oral contraceptives and her family history. So the risk stratification, both in the low penetrance gene like the prostate GWAS and in the situation of high penetrance genes, can get quite complex. And so we're starting to think, when we say precision medicine, we're starting to think about really, really complex, potentially clinically difficult. How are we going to present this information to not only a clinician but the patient, so that they can make informed decisions about something that's quite complex around biology, mutational status, and all that sort of thing? Is that feasible? Is that something we can and should do? But just so that you can see, it's likely to get quite complex when we talk about precision medicine and precision prevention. And so we need to be prepped for doing good studies that will allow us to make these inferences, and then also the translation of this information into a clinical or public health setting. So, in summary, precision approaches may complement existing prevention and early detection efforts. So I wanted to be really clear, I'm not saying that these molecularly based, precision-based methods should supplant tobacco taxes or low-dose CT screening for lung cancer. What they should do is be an adjunct, an additional tool that we have in our array to prevent cancer in certain situations where it's valid. Precision strategies allow us to move away from the equal application of interventions and toward more equitable outcomes. Again, not applying oophorectomy in a BRCA1 mutation carrier to all, but maybe applying it judiciously based on the complex nature of an individual woman's risk and choices and behavioral profiles. So the precision strategies may help us to focus on at-risk populations and then motivate them to engage in prevention strategies. So again, if you know that you're at really high risk, if you can be convinced that your risk is sufficiently high, that you're willing to take on a higher level of toxicity or risk in the preventive strategy, that may help motivate people. It may help get increased compliance with the prevention strategies in some way. And again, diversity of research participants and the setting is really required to optimize these approaches. There's a great paper by Zach Kohani's group in the New England Journal of Medicine this past a couple of months ago, where they did genetic testing. It was in cardiomyopathy, but they did genetic testing in a diverse ethnic population, and they found that if you only tested Caucasian individuals, you would infer a certain number of mutations to be deleterious disease-causing. But when you tested them in a diverse population of African Americans and Asians, you learned that some of those variants in the Caucasian population were just rare common variants that were extremely common, say, in African Americans. They weren't deleterious at all. So there were really important mistakes that were made in genetic diagnoses by only having studied a Caucasian population by expanding and understanding the entire population, you now are able to see the full picture of frequency and evolutionary events that contribute to the risk and better diagnosis. So I think that there's a lot of reason for thinking about diversity, not only the important reason of making sure that all populations are part of research and benefit. And let me just end by saying, too many people to list who are on the work, but I appreciate your attention. Thank you.
Yeah, time for a few questions.
Yeah.
Excellent presentation. I was struck by the relative risks, and when you made the point that genetic testing on the population isn't adding that much oomph as we had originally had thought, and then you're discussing the implications for the future for precision medicine. So what is the vision as you think forward in terms of research? Because I always said it's really cross-cutting, is how do we get to precision medicine from where we are?
Yeah, and I didn't want to leave you with the message that common genetic variation and polygenic risk scores have no value.
Right.
But they don't have the value that we expected them to. And they're not necessarily going to solve all our problems, which again, isn't really a surprise. So I think the question is going to be, we have a lot of data and we have a lot of information. How best do we take that information into something that's going to be actionable and useful? And I don't have the answer to that, but we have so much information now. We're learning what that information is good for and what it's not good for. And now that we've done 8 bazillion GWAS studies and we have lots of SNPs out there, the next step is going to have to be studies of, not discovery, but translation, about what the meaning of that information is and the value in terms of making decisions or applying interventions appropriately. And I would say almost none of that work has been done. So, yeah.
Tim, thank you for a great talk. The genetic high-risk approach and also the myeloma antibody spike approach, both assume that you know who has the spike and who has the mutation.
Yes.
So that may imply actually a broad population search. In which case, this high-risk approach is at least partly population-based in order to find out who is at high risk.
Yeah.
So for BRCA, I don't know the answer, but I'm guessing that quite a few BRCA carriers aren't identified from family history.
Right.
So how would you then translate your BRCA approach?
Yeah.
Into a practical approach identifying those high-risk people.
Right. So the points you make are absolutely correct, that what I presented today is sort of discovery based on sets of individuals who have been identified for MGUS or BRCA based on some characteristics that we can readily identify through research studies or clinics or whatever it might be. And that isn't where we need to stop. That's sort of the way discovery of these phenomena have been done. And so when we want to take it to its extreme, it does become a population approach. But on the other hand, it can't be a population approach. You can't necessarily do this on everybody. Some people will argue, if you're Mary Claire King, you will argue everybody should have BRCA1 and 2 testing, particularly if you're Ashkenazi Jewish. And that's a reasonable argument that can be debated, assuming that there's enough resources to do it, because it's common enough and it has actionability. In MGUS, you certainly could test everybody for M spikes because it's cheap and we do tests like that all the time. You wouldn't want to do that because you're going to find a lot of M spikes that are not going to go anywhere, so you'd have to have the associated education and everything to not worry people that they're about to develop myeloma tomorrow. So the implementation of all of that is really very critical. And the other piece to that is that now, of course, what people do in the clinical genetics setting is panel testing. People don't test for BRCA1 anymore. They test for mutations. And as you test for more mutations broadly in the population, you find them. And so then the family history positive people that look like they should be BRCA1 carriers, sometimes they're PALB2 carriers. And it's a completely different thing that you have to then deal with. So the information that you're gathering through more extensive genetic testing and molecular testing across populations has to be accompanied by tools that either allow you to, the patient and the clinician, to understand what it means and what it doesn't mean and have it interpreted correctly, or find algorithms that will allow you to only test those people that really need it, whatever that may be. So that's the non-answer to your question, because I don't know what the answer is, but something like that has to happen.
Great, thanks again.